Okay, I'm delighted to welcome Professor Krishna Kavi from University of North Texas, Department of Computer Science and Engineering. Nora Jones graduated from University of North Texas.
And Don Henley also, of Eagles.
So, Krishna has been director of the NSF Indiana Industry University Research Center. He was department head in computer science and engineering at University of North Texas and has done amazing work in hardware, machine learning, security. So I would welcome you to go to his webpage and read all about it. And also I will let him get started on his presentation.
I think Thank you, Bharat. I don't know how many of you have hardware background in terms of actual processors and how pipelines work and how cache memories work. So what I'll do is I'll give a brief introduction to how they work and how those features expose the hardware to security attacks. So my talk is on hardware side channel attacks. Most of you probably know what a side channel attack means compared to direct attack. So side channel indicates that you observe certain properties about executing programs, and based on observation of those properties, you try to derive some secret information from the application itself, the program itself. So some examples of side channel are properties that you can observe is execution time of a program. So how long did the program take to execute? Based on that, you can predict which branch was taken, what value. So for example, in this, I don't know if you can see clearly, but you have branch paths there. So depending on execution times, you can find out which path was taken. And based on which path was taken, you also know what's the condition value at that branch. So that's one type of attack so you can predict. So for example, you can say in the branch, was the value 0 or greater than 0? Maybe there was a condition used, so you can predict which value was used. So those are called timing attacks. And there are other types of attacks people have actually were successful, which is power and energy attacks. So you can estimate how much energy was consumed by your application. Even based on that, you can predict what was the execution path, what were the values used, and those kinds of things. Or you can find out how many times a loop was executed. If the loop is executed longer, then it will take longer, it consumes more energy, and so on. And there were even some attacks observing electromagnetic energy emitted by your screen and then predict what was the actual values typed on the screen. So those are the examples of not interfering with the actual program execution, but observing properties. So what we are going to look at today is mostly based on timing attacks and a few other properties of the hardware. So there are two things that I'm going to focus today on. One is cache memory. The other one is speculative execution. And those are the two architectural features. I won't call them weaknesses, but they're features of the architecture that were used to exploit Spectre and Meltdown. So let's look at how cache memory works. So if you're given an address, you're going to use a certain number of bits from the address. And can you see? Okay. Is this the same screen that you're seeing? I don't know.
Yeah.
I assume, okay. So as you can see, the middle bits, those 10 bits of an address, are used to locate a cache line, to find out where your data is stored in your cache. Those are called index bits. All caches use the same set of index bits. So an attacker can evict your data as long as the attacker's address matches the index bits of the victim. So you can evict them, right? So that's one of the properties people exploit. Nowadays we have something called set associative cache. Basically, set associative means an index identifies a number of cache lines, which is called a set. In this example, we have 4. So one index identifies 4 lines, so your data may be in one of the 4 locations. But again, we are using a certain number of bits. And in most cases, we're using those bits so that we can use the modular arithmetic. So hardware is simple, so we can use those 4 bits, of those bits, index bits. So again, because any address uses the same mechanism, an attacker can evict victim's data, and by evicting, you can find out if the attacker has the same index bits or not, and based on that, you can exploit. I'll give an example of an exploit. Let me show you. This is called Bernstein's attack. Was exposed about like maybe 10 years ago. So basically, if you're using encryption based on AES, most implementations of AES, what they do is they pre-compute some values and store in the tables. And you'll find out those values of the table by using an exclusive OR of a portion of the key, usually 8 bits of the key, and 8 bits of the plain text. That will give you an index into the table so that describes some computations pre-computed on those values, because otherwise it's going to take a long time to compute them, right? So now the table will go into a cache, because table is data, contains data, so you have to bring the data into your cache. Once it gets into the cache, you're going to index it, you're going to find the entry, right? So based on index use, you know something about the key and the plain text values, because that's nothing but exclusive OR of those 2, right? So you can do this several times to find all the pieces of the key. So that's what Bernstein's attack is. And this is part of also the current Spectre attack. So once you get the data into cache, you can use these kinds of attacks to reveal that information. So that's it. I'm going to go through it quick. So in order to perform these attacks, it's not that easy, but what you have to do is you have to have patience. You have to try several times to evict the right amount of right indexes, right entries in the table, and you have to repeat it several times, because each time you only get a portion of the key, so you have to repeat it several times to find the entire key. You also have to know if the data is evicted or not. So you have to know if cache entry is evicted. If the cache is evicted, it causes cache miss. If it causes cache miss, your program takes longer to execute, right? So you have to be able to measure execution time in a very fine-grained level so that you know if the cache caused a miss or not. So these are not easy, but they're doable. If you have the patience, if you know how to use the right tools, you can do that. So these are tools which are available to anybody to use in Linux. So hardware has something called performance counters. So you can use performance counters to measure how many cache misses are caused by your program, how many times an AND instruction was executed if you want, how many times a multiply instruction is executed. All of those are available so that you can optimize your code, right? So those are made available for good reasons, but people can use that to attack. So there are 3 types of cache attacks that are commonly grouped together. One is called prime and probe. This is generic name. Prime means the attacker fills the entire cache. Every single line of the cache is filled by attacker's data. So cache is fully full, right, with the attacker's information. Now, when the victim's program starts executing, victim needs to replace the data, so because he has to bring, the victim's program has to bring its own data. Now when the attacker comes back and tries to execute, he can discover that some of his data has been evicted, right, because it causes cache misses. Based on that, you can know exactly what data items are evicted, and based on that, what is the index. From that, you can get additional information of the victim. So that's called prime and probe. It's prime because you're priming the cache by filling it fully with your data, attacker's data. The second one is called evict and time. This way, you don't fill the entire cache. You selectively evict victim's data. So you just basically try to store some data into cache line, and then if that causes a miss for the victim, then you know the victim accessed that data item, right? If a victim accessed the data item and you evicted that, so victim is going to take longer, so it's going to cause a cache miss. So that's also, you can time it and find out which lines the victim may have accessed. So this type of attack called evict and time. So you're selectively evicting. So you can start evicting one line at a time. If the attacker used that line, that means victim uses that line, the victim is going to cause a cache miss, it's going to take longer. If victim did not touch that line, it will not cause a cache miss. So you know that victim did not use that address. The third type of attack is flush and reload. This is particularly useful if you have multi-core processors, so you don't have to run on the same core as a victim. So your attack program doesn't have to run on the same core as a victim. In multi-core, using this, you can evict all the caches for everybody, including every course cache plus shared cache. So this is called flush and reload. So you're going to flush all caches. And that can be done using a simple Intel instruction called CFlush. So if you use CFlush, it evicts all the caches. So you can use that. This way, you don't have to run on the same core as the victim and still observe properties. So those are the three most commonly used types of cache attacks. And actually, this last attack can be used to reveal which pages are used or shared by the victim and attacker, because operating system and other libraries are shared by everybody. So you can find out what portions are used. And the types of solutions commonly used for this are, I group them into two types. One is partitioning, the other one is randomizing. These are the two solutions people have been talking about. Partitioning, as you would probably envision, is dividing the cache into different parts and run different programs in different parts of the cache so the attacker cannot evict. So for example, there are several proposals. ARM, if you use ARM processors, and ARM, if you're using the ARM trusted zone, which supports trusted support, if you're going to use trusted zones for running applications, each application is going to be flagged, whether it's a secure application or not. So the cache will also be flagged with 1 bit saying that this cache line belongs to a secure application or non-secure application. So the attacker, if he's running in a non-secure portion, will not be able to evict secure lines. So ARM claims that you can't evict our lines, but some people have. Can you hear?
No, he's typing something and I can't hear.
Yeah, okay. Okay. So there's a paper recently showing that ARMs, that the 1 bit indicating whether a secure application or not doesn't protect, because we talked about prime and probe. Prime means it store the entire cache before the secure application is loaded, right? So you already occupied all of that. When the secure application comes, the attacker's lines are still evicted. Even though you cannot evict a victim's lines, your lines are evicted, so you can still find out from there. So they have proven that this doesn't really protect. So the other way of dividing cache is just partition the cache and say these cache lines belong to secure application, these are belong to non-secure applications. Remember I talked about set associative caches where you have several lines together, one set. So recently a paper from MIT, just in this December 2018, they proposed using different lines in a set for secure and non-secure applications. So in this example, there are 8 ways. That means 8 cache lines together has 1 address, 1 index. Those are called 8 ways. So for example, that red ones, W0 and W1, are allocated for secure applications. The others are not. So you will never be able to touch those two lines. You will not get any information about those two lines. But again, the prime and probe is not protected by this, right? But when you prime, you fill the entire cache, so you can still find out that somebody evicted your lines or not. So the other type is randomizing. So one proposal from Princeton several years ago is to use an additional table called permutation table. So you take the index and use the index into a permutation table, and the permutation table gives you some new random address. So use that random address for cache. So even though attacker and victim have the same index, they use different random numbers to say where the data is placed. So this way, attacker does not really know by evicting a cache line that the attacker and victim has the same index, because index has been changed. The main problem with this one is you have an extra table that you have to look up. So you cannot access cache directly. So you have to use the index, then go into the permutation table, and then go to the cache. Cache, the reason why we use cache is because we want to make memory access very fast, right? By adding this extra layer, your speed is going to go down, right? So you're losing performance by doing this. The second thing is somebody has to load those permutation tables. So every time you start running your program, you have to first fill these permutation tables, right? So that's an extra overhead. So what we proposed is a much simpler solution. Just change which bits you are going to use for index. Why do you have to use the same bits for everybody as an index? Remember I shown you those 10 bits in your address as your index? Why do you have to use the same 10 bits? Why not use some different combinations of bits? So the victim, you will use a different set of bits, and attacker will use the different bits, right? So no two programs use the same portion of your address. That way you won't be able to predict, right? So this way you don't have to change the extra hardware. You don't have to go to another table to find an index and so on. So by just changing the bits, we get the same effect of randomizing. But which bits do you use, right? So we studied different solutions. One solution we did was take the standard index bits and take some bits from the tag and exclusive order them. So your tag would be different from attacker's tag because those addresses will be different. So just take an exclusive order them, you can create a new index. So it's a very simple solution, right? The hardware is very simple. And you can think of other ways. I'll show you some data quickly. So we studied this. How much performance are you going to lose or gain by using this method? So we studied for several benchmarks, and we ran it on a 4-core system, assuming 4 cores, and 4 cores running 4 different programs. Each program you use slightly different indexing method, saying that how much performance are you going to lose by doing that. This shows how many cache misses are caused, what's the miss rate at L3, shared level, last level cache. As you can see, the difference is not significant. So the first line, the blue line to the left in each of those sets of data is original. That means no standard indexing. And the other things are slightly different variations running on different types of processors, whether AMD processor or Intel processor and so on. As you notice, the difference is not that significant, so you're really not losing significant performance by changing the indexing. We also studied the actual execution time. So again, for the same benchmarks, how much performance are you losing? So as you can see, the performance loss is 1% or 2% in that range. So we feel that this is acceptable performance loss that you can tolerate but achieve security against cache attacks, right? And we tried other type of solutions. Instead of exclusive ORing, can we use an AND? Can we use a NAND and stuff like that? Of the index bits plus some tag bits, do you exclusive OR? Do you AND them? Do you OR them? And so on. But we found out AND is really bad. So if you use AND, the performance loss can be significant. Whereas exclusive OR is very good. Exclusive doesn't lose much performance. But if you do and, you lose quite a bit, as you can see. So what we need to do is try different combinations. Here shows performance loss and so on. So what we need to do, so what we need to do is study different ways of changing indexing, randomizing it, so that every time your program is loaded, operating system decides what index to use, right? And it can change randomly. So now attacker would never be able to predict if you have the same index bits or not. I mean, you can predict because there are a finite number of combinations. If you run 1,000,000 times, you can still predict. But you're making it so much more difficult for the attacker. The second type of attack is primarily based on speculation. So when you talk about timing analysis, the timing is based on the fact that all architectures use speculative execution. So let me talk briefly about what speculative execution means from architecture point of view. If you've taken any architecture class, you must have seen this diagram, right? This is from Hennessy and Patterson book. So you have the five pipeline stages: instruction, fetch, decode, execute, and so on, right? So if you have a branch instruction, you know the branch instruction is being executed in the decode stage, right? When you decode it, you know you have a branch instruction. But you have to wait until execute stage to find out if the branch is going to be taken or not taken. So if you don't do anything, you're going to lose 2 cycles, right, in these five pipeline stages. But most of today's architectures may have like 20 stages of pipelines. So branches can cause about 20 cycle loss. So in order to avoid that, what we're going to do is we're going to predict whether the branch is going to be taken or not, even before we know the decision, and start executing instructions from the predicted path. That way, if you're correct, you won't lose any cycles, but if you are mispredict, then you lose cycles, right? So then the goal is to make your prediction as accurate as possible. So here is an example. Simple loop, you have you're incrementing an array by 1, right? Simple loop. So when I say speculative execution, here it shows when each of the instructions is going to be completed. Look at the last column to the right, just before the comments. Commit, it says commit at cycle number. So that indicates when the instruction actually completed, right? Now look at load instruction from the second iteration. So if you look at the iteration number in the first column, so second iteration, the load instruction should not start until cycle 9 executing, right? Because the branch from the first iteration is not completed in cycle 8. So you should not start load until we know that branch is going to be taken and start executing next iteration in cycle 9, right? But what speculative execution say, hey, this is a loop, so chances are you're going to repeat it. So it's going to predict and start executing. As you can see, it started executing in cycle 5, load from the second iteration. And if you're lucky, if your branch is going to be taken, everything is going to go well, right? You saved, instead of waiting until cycle 9, you started executing cycle 5, that means you saved 4 cycles. So that's the idea behind speculation. You have a question? No. And what's more interesting about this is where the security attacks come into play. So let's look at this example of a loop. This loop should only execute 100 times, right? When I equals 100, what happens? We should not execute. We should not execute next cycle, next iteration, right? But what does our speculation do? In the 99th, when I equals 99, and when next cycle comes, we predict that you're going to take the branch, and we go ahead and execute it. What happened then? You fetched B100. You're not supposed to get B100. You already got B100, right? The system says, hey, this is wrong. You should not execute it. Whenever we get the data, it goes into the cache. the data. If it is not in the cache already, you bring it from memory into the cache. So when I say load, I'm bringing the data into the cache. Even if the program says you should not fetch this data, you are not going to take the data away from the cache. You're going to leave the data in the cache. Now the attacker has access to that data because you can use cache attacks to reveal that information. So that's the attack that Spectre and Meltdown uses. So basically, it knows that you're going to execute speculatively and try to execute illegal operations. And it's going to fetch the data. So for example, you're not supposed to access kernel tables, right, from the user code, but try to get the data from the kernel tables, and the speculation may get the data for you already, even though operating system will kill your program. Then you can use a different program to reveal the information from the cache. So you can have two programs on the attacker side. One to try to illegally get the data into the cache, and another to reveal the data from the cache. That's how Spectre and Meltdown type of attacks work. Again, it's not easy. You have to try so many times to be able to get that data. So again, that's how these two attacks work. And again, these are because how cache memories are designed, how speculation works, right? So basically how the speculation works is you have a table called branch prediction table, and you usually use 2 bits in the branch prediction, saying that if branch is predicted correctly or not. If you mispredict a branch 2 times, then we change the prediction. There is a reason why we wait for 2 times to be mispredicted, but that's, if you're taking architecture, you probably know why that is. So we use 2 bits, and you use the same prediction unless you mispredicted 2 times in a row. If you mispredicted 2 times in a row, we change the prediction to the opposite. So if you initially predicted branch is going to be taken, and you mispredicted 2 times, you change it to branch not taken, right? And the next thing we also do is we have this table called a branch target buffer. So what this branch target buffer does is I guess, can you see my cursor? No? Oh, okay. So you have the address of the instruction that you're going to execute if the branch is taken. So this table contains the address where you're going to jump to if the branch is taken. So if you predicted branch is going to be taken, you already have the address of where you're going to branch, so you can start fetching the instruction from that address and start executing. So you won't lose any cycles. So that's why we need this table, and this table is going to be indexed by the branch instruction. So in the previous example, we have branch not equals. So the branch not equals instruction has an address, the program counter address. We use the program counter address and use that as an index into this table. This table tells you if the branch is going to be predicted as taken or not taken. And if it is predicted as taken, then we also have the address or where you're going to branch to. See, so you have all the information you need to start executing immediately the next instruction. But once you start executing instructions speculatively, we need to make sure that if the prediction is not correct, we have to undo all the computations, right? If the branch is mispredicted, you have to undo add instructions that follow or multiply instructions we follow. So what we do for that is they have a buffer called reorder buffer. So if you see on the right-hand top, there's a reorder buffer. So all the instructions except load and store their results in this buffer. Only when we are ready to say that branch is correctly predicted, so these instructions are correctly executed, we won't copy that data into the right locations. So we buffer the data into the buffers until we know whether you executed correctly or not. However, load instructions still get the data into cache. So some new solutions. Oh, by the way, one of the things we did was, what if we randomly make the architecture mispredict? So remember we talked about timing attack. Timing attack is assuming the branch prediction is correct and works normally, so you can find the times. If I force the hardware to mispredict randomly, I'm changing the timing, right? So that it will become more difficult for timing attacks to know when I made the architecture to mispredict. So one way to do that is just clear the table bits, right? If you remember, we had the 2 bits for branch prediction, right? Periodically, I'm going to reset to zeros, all of them. So the hardware mispredicts, right? So depending on when I reset it, the execution time changes completely. So the timing attacks become much more difficult. So here is an example. If you look at the table I've shown you in the 2 columns there, one column says that if your prediction is correct, how your instructions are going to look like when they're executed. And on the right-hand side, I'm going to make it mispredict. So we're going to say that branch is not taken, so even though loops normally take, I'm mispredicting. So it shows how the instructions look like when they execute based on misprediction. So as you can see, the number of instructions executed, number of cycles needed will be completely different, right? So we can think of randomly clearing the table, right? So what we did was, what if I cleared the table for every 10,000 instructions, every 100,000 instructions, every million instructions, and so on? How much performance am I going to lose? If you clear the table more frequently, you're going to lose more performance, right? So effectively, if I clear every cycle, what's going to happen? It means like you don't have any speculative execution, right? There's no speculation because you're mispredicting every time. So we can do that, or say never clear, then it's going to have full speculation. So you can change randomly how often you're going to mispredict. So if you look at, I don't know if you can see the data. So if you mispredicted every 100 million instructions, you only lose like 0.1%, whereas if you cleared it every 10,000 instructions, you might lose about 10%. So you have a range on how much performance are you willing to lose, how much more difficult you want to make for the timing attacks. So you can change that, you know. So again, we need to look at many more solutions, many more simulations, more examples, more tests to do this. So we're working on that. And we want, actually what we want to do is launch Spectre attack and find out the timing differences, how much more difficult would be to predict, how many more times you have to use this Spectre attack before you reveal the information. And the next progress in trying to mitigate the attacks, the solutions for this is, can we somehow make this speculative load not visible? That's why we call silent speculative loads. That means treat whenever you're loading the data speculatively to be different from normal load instruction. Remember, when you have speculative load, the data comes to the cache, right? That's how the attacker reveals information about the data. So if you bring it into the cache, even though that load should not have been executed, the data is already in the cache. And there are other type of things that happens when you bring it into the cache. There's something called metadata that is also going to change. Metadata is like, for example, when was this cache line last accessed? So we have the LRU bits, least recently used bits, which are used to find out which cache line you're going to evict, if you have to evict. So that's called metadata. And there are some other things, coherency. If you two cores share the data and one core writes, you had to invalidate the other data and so on. So those kinds of coherency information is also called a metadata. So if you bring the data into the cache, you may change the metadata or actual cache data. So can I go back to my slide? So there's a paper, again, appeared in December this year. What they're proposing is use a buffer for load. So don't use the cache memory when you're doing speculative load. So you have a separate buffer, so you bring the data into the buffer rather than into the cache, so that if you mispredicted the cache data, that's not going to be visible in the cache. So attacker would not know that you actually read that data. So you have to have an extra buffer. But this causes some problems. So for one thing, it causes performance, because if somebody else accesses the same cache data, you have to go back and read from memory, because that still will be as a cache miss. So you have some loss, because if you brought the data into the cache, you would have avoided one cache miss, but now you're causing additional cache misses, so you lose some information. But more significant is, how do we handle cache coherency issues? So let's take an example. I've shown you here 2 cores, right? Let's assume that both cores share the same data. That means they access the same cache line, same information. Core 1 gets the data speculatively, so it comes to the buffer, and cache is not being modified. So core 2 does not have any information that core 1 accessed that data, right? Suppose core 2 gets the data and modifies the data, right? What should happen to the data in the buffer? Should it become invalid because core 2 already read the data, or should we say that core 1 actually read the data before core 2, so the data should be valid still? So we have to make decisions as to saying that which one will we invalidate, right? So that's called memory ordering. So we have to find out who read first, right? Which order should we use? So I think, let me see. So here is a timeline if you want to think of. So we have a speculative load first in core 1. And then sometime later, the second core read and modified the data. And now the speculation was correct, and core 1 says, okay, I'm going to use the data. So I read the data before, so all the instructions use my old data, right? But that should be invalidated because core 2 modified the data already by that time. So you have to kill everything you have done, because your data is no longer valid, even though you read the data first, right? So you're going to cause a lot of performance loss, because the way this solution, this paper talks about is, when you commit, when you're ready to commit the load instruction, so far nobody knows that you read the data, right? So you need to make everybody know that you read the data. So they issue a normal load second time. So first time you have speculative load, you got the data into your buffer. When you're ready to commit, you again issue an instruction, say, I'm reading the data now, right? So that everybody can see it at that time. And at that time, the second core says, hey, I have a new data, by the way, read this data. So now we have to invalidate all of that data. But today's processors don't do that. Today's processors, because they read the data is already in the cache, so core 1's read precedes core 2's modification. So core 1 is allowed to use the data because it's read before, right? So today's architectures use a different memory ordering, and this new idea will use a completely different memory ordering. So which one will people accept? Because if you run on one system, you might get different answer compared to running on a different system. So you might have different ordering. So people have to explore how this is going to impact your correctness, program correctness, and all of those. But this is a good solution so that we can make the loads, speculative loads, invisible. Actually, we were working on it, and then suddenly these people beat us to the deadline, so they got the paper out than we did. So we had exactly the same solution we were exploring. So what we are going to look at is, I don't know how many of you know the transactional memory models. I was going to talk to Dr. Obergawa about saying that architecture also uses transaction models, concurrency models, and stuff like that nowadays. So basically what we want to do is look at a sequence of instructions as a single transaction, right? So all the instructions in that sequence will either commit or do not commit. So they have to be all committed together, or none of them will be committed, right? So in architecture, if we start doing that, we can say that a sequence of instructions which are executed speculatively will be a transaction. So if we find out that your load is invalid because somebody else modified the data, we're going to kill all the speculatively executed instruction. So we're going to keep it in a buffer. So we are exploring, saying that we want to extend that other paper where they're looking at only single speculative instruction, but we want to extend the whole thing make it as a transaction. So look at speculative execution, convert that into a transaction model, and find out how much performance you're going to lose, how the solution works. So that's what we are working. Hopefully, they won't do the same thing before we do. So one final thing, I just want to talk about hardware level security issues. Most of today's processors, particularly Xeon processors, use hyperthreading. So hyperthreading basically means on a single core, they can mix multiple threads together and run it through the pipeline. So you can have 4 threads. Sometimes you might see that 10 cores, 40 threads. That means each core can run 4 threads at a time. And they mix together those instructions. When you mix those instructions, there's a problem because they share certain tables. They use TLB tables, for example, transaction look-aside buffer tables. So now one thread running on the same core can try to get information about the TLB entries of some other thread. So now we can actually reveal page table information, which is very, like dangerous. There are some attacks. That's one of the reasons why Coffee Lake now has 2 options. Latest Intel 2 options. Either you can buy one which enables hyperthreading, one which doesn't. So if you want a more secure, buy one without hyperthreading. You might lose some performance, but at least you can avoid some of the attacks. So they give you the option of doing that. So that's what I wanted to talk about today, basically about what side channel attacks on hardware level means, give you an idea what features of the architecture enables those attacks, and what is the current thinking in protecting it. By the way, there's no software solution for these. You cannot prevent these attacks by simply using software. So we have to change the hardware. So Intel has to get rid of all of those over a period of time. Until that time, any Intel processor is prone to those attacks. So there's no software solution for this. So Intel knows that. That's why they're working on it. So thank you.
To press and then push to ask a question.
Any questions?
I have one question. It's not really a software solution, but it's a solution without changing the hardware, which is basically you cannot allow untrusted code to run on your hardware when you're running something that you're concerned about. That basically you're saying all code is trusted.
Right, so attackers' code can be trusted too, in principle, because all they're doing is loading and unloading data, right?
So that's what I mean. It's not that attackers' code is, it is doing something. The question is who's it trusted by? I mean, it's like if I have all my own code that only I have created, right. I've checked it out. Right. And nothing else can run on the processor at the time, then this should...
So I can write a matrix multiplication, and at the very beginning I can create a loop. All it does is clears all my huge matrices, right? What's happening to the cache then? So my code is perfectly valid code because I'm writing this huge matrix multiplication which multiply million by million, and at the very beginning I cleared my matrices. That's enough to clear all the caches. Yeah.
So in other words, it's very difficult to validate that code would not be performing this attack.
That's correct, right. So that's what attackers use, because you cannot, none of the verification techniques you have in software will be able to say with confidence that this could potentially be a side channel attack. So that's why I was talking to Intel. Yeah. Intel said, is there a way we can detect a side channel attack? Right? The only thing you can do side channel attack is, if the side channel attack is causing more cache misses, maybe you can say that there's something wrong here, right? Normally, your system should not cause this many cache misses. And suddenly, when two programs are running, it's causing a lot of cache misses. So there's something suspicious, right? That's all you can say. Beyond that, you don't know what's happening. So yeah, Intel was looking at, is there a way to find that there is a side channel attack being happening right now? So
well, it does require though that you have another thread or process running on the processor before yours has completely finished its task.
That's one of the reasons why hyperthreading. Some people now saying that I don't want to use hyperthreading.
Yeah,
but
because
remember,
this doesn't require hyperthreading, but it does require something else running on the same processor.
It doesn't
right?
have to be in the same processor. Remember, there's something called CFlush, which evicts all the cache lines every place.
Okay, so it's not even on the same processor;
right,
it's on the same
multi-core,
system.
Right. As long as the multi-core clears all the caches.
Well, no, I'm not saying not same core.
But I'm saying if a multi-core processor, if you're running on a different core, you run.
So it's not, but the processor itself. If I run that I have a completely independent processor, that there's nothing running on any of the other cores.
Yeah, then why would you want a processor with that many cores and not use them, right?
Yeah, exactly. I'm just saying that from Intel's point of view, maybe these, if that's the solution, then you sell more processors.
Yeah. So that's why if you're running, you're the only one user.
Yeah.
I have 32 cores, but I'm only running one.
But basically, that's the only solution at this point is that you have to be the exclusive user of the processor.
What they're trying to do is all these different solutions, saying that I want to make sure that secure applications have reserved cache lines, even though not all attacks are prevented. Some attacks are prevented. Plus, most of the Unix, they have the deduplication. For example, when you have two programs running, they share some tables, right? So some pages, common libraries and so on. The reason why they do that is you don't want to duplicate and waste memory. That's what it's called deduplication, eliminate duplication. But there's a flag in Linux saying that I want duplicate copies. So eliminate deduplication, so that you have a flag to say that I don't want to use somebody else's. I don't want to share somebody else's libraries. Give me my own copies, right? So you're willing to lose some performance because of that. So there are some people thinking about how do we do this, sacrifice some performance, but try to mitigate the attacks. Mm-hmm. But the Linux solution, when they first came out, as soon as Spectre attack was revealed, Linux said that you can use this. Then immediately they said, "Oh, we're losing 40% performance. It's not acceptable." But the only solution is change the hardware. Yes.
So if you have like an isolated memory for each of the applications, so even if you lose some performance, even if you lose some performance, all these attacks will not work, right? Like for the meltdown attack, it just had a software fix where you just make the user applications and the system applications have completely different memory. So this should work, right? What kind of attacks will this not stop?
But because speculation, you cannot prevent the speculation where even secure cache lines will be brought into the cache, right? So the data will be brought into the cache. Even though you're not allowed to access it, you can illegally try to get the data. System will abort your program, but the data is already brought into the cache. So that's the reason behind speculative attack and Spectre meltdown. Those cannot be prevented. It's going to be more difficult. It takes longer time to do that, but you cannot prevent unless you modify the speculation somehow. So we have to address the idea of, if I'm doing speculative execution and if I'm going to read the data, should I reveal the data or not, right? So right now you're revealing the data because you're bringing it to the cache. And that's the reason why the last 2 slides I talk about making the speculative execution silent, speculative load silent. That means if you bring the data in a speculative mode, don't change any system state. So actually what we want to do is formalize this, saying that in any hardware, if I do something, what changes are observable in the system state, right? So what I want to see is, if I do something speculative, I want to make sure that my state changes are not observable by other people. So how do we do that? How do we design such that if I do something to speed up, I don't want to reveal that I'm doing that. I don't want that information to be revealed. So what we're looking at, what are all these state changes? For example, I didn't talk about there, one of the things nobody has talked about so far is performance counters, right? So performance counters, as I said, counts how many times your cache misses, or you can even count how many times a branch instruction is executed, how many times a load multiply instruction is executed, right? Even though I hid the information that I did something speculative, your performance counters are still counting how many times your load instruction was executed. So what we want to do is make sure that the speculative load doesn't even change this performance counter, right? So we have to think in terms of what state changes are happening whenever I execute something. I want to make that as silent, as non-observable as possible, so the attacker cannot use side channel attacks. Remember, side channel attack means observing something. I want to make my speculative execution as unobservable as possible. Any other questions? Because I have to run and try to go all the way to Indianapolis to catch my flight. So. But please send an email or any other questions you may have.